AJ Kantor, we're going to talk nuclear now, which I'm very happy about because it's a really important area of climate tech. And AJ is chief of staff at a company called Zap Energy based in Seattle. She was at one time a longtime person at Tesla. Then she went into VC. But in the course of your work in VC, you kind of realized this climate thing was what you wanted to act on. And then how did you get to nuclear, though? Personally, just quickly.
The short story is I was working in general on kind of what could the grid potentially look like, what should it look like, what might it look like. All of those are very different things in the world of investing. And what I ultimately came to is, a distributed nuclear fusion solution would be a solution at the scale of the problem. And I think that, when you think about what are the most investable areas, the most investable areas are where you can build megalithic companies and where you can make a really large impact. And I came to that conclusion after probably a year of deep dive work. Ultimately, there will be a number of solutions that ultimately add up to the kind of final way that we can address kind of anthropogenic change in the climate. But fusion, I can see being a very large part of that.
So you decided fusion was the area, but then you researched all the fusion companies, right?
Then I looked at all the fusion companies, of which there are about 25 in the Fusion Industry Association today. So
those are all startups pretty much, but very heavily funded in many cases.
Yeah, $4 billion of investment in the last
$4 billion into
years.
25 companies. Okay.
Yeah, so not in.
But none of whom anybody here has heard of unless you're an expert in the area, because none of them have really accomplished anything yet. But go on. Sorry, even including you, but go on.
Yeah, so that's a very good point. Fusion is a new industry. It's been an ongoing science project for the past 60 years, but it's consistently, there's a joke that everybody says about the fusion industry, it's always 20 years away. I think what we're doing now, a lot of these companies in the game are trying to challenge that adage.
Well, I was telling you about my friend who lives in Munich who left journalism to go to work for a German fusion company, and she was describing their, laser and how they're trying to get the state of Bavaria to invest, 100 million euros to get their test facility off the ground. But you guys have a very different approach from anybody else, which is fascinating. So describe how Zap Energy differs from all the other fusion startups.
Sure. Yeah, so I'll start by just explaining how fusion has been done for the past 60 years, clearly without much fruit. There are two main approaches that are used. One is called inertial confinement confusion, inertial confinement fusion, which essentially uses football fields worth of lasers to shoot all these lasers at a tiny little deuterium and tritium pellet. And it's more of a kind of science project approach, being able to prove that fusion, understand how it works. The kind of status quo for doing fusion today has been magnetic confinement fusion, which uses a device called a tokamak, which is essentially a giant donut-shaped accelerator-type device that is on the order of hundreds of millions of dollars at its smallest, and ITER in southern France is a $22.5 billion project.
Which still hasn't succeeded in making fusion energy.
Which has not yet met energy break-even, which I'm sure we'll talk about. The issue with these two approaches is that they're not scalable. If you're trying to put fusion energy on the grid, you need something that has viable unit economics. And if you're talking about building something with a reactor core that's $400 million, it's hard to say that you're going to get something with an LCOE that's viable.
LCOE is
levelized cost of energy.
Okay.
And so you're really trying to address how do we actually build fusion for the grid, not for a science project. And what we do is something called sheared flow stabilized Z-pinch.
You don't have to define all of that, but go on.
And the short of it is, what makes those $400 million tokamaks $400 million in large part is the magnets that they use. So they use magnets to suspend, confine, and compress the plasma to get it to fusion conditions and have it put off neutrons. What we do is just get rid of the magnets in order to do magnetic confinement fusion. So you've probably heard of a Z-pinch, from whatever EE class you've taken. You pass current through a conductor and you generate a magnetic field around it. And so that's what we do. We use this very well-known bit of physics And we optimize it by putting a sheared flow in the actual column of plasma to keep it stable for long enough to get a really viable fusion reaction.
So assuming you can make it work, which I know you're confident of, what would be the cost comparison of your system if it works compared to pretty much any of the other 24 companies?
Yeah, I mean, when you think about the fact that these magnets are adding up to hundreds of millions of dollars, when you get rid of them, you're talking about a reactor that's 2 orders of magnitude less expensive for the same output. So we're probably something on the order of 4 million rather than 400.
So what is Zap Energy's view and what is sort of the industry consensus of whether and when we will actually get positive energy out of a fusion process?
Good question. So just to contextualize for everybody, fusion has yet to meet something called Q equals 1, energy break even. So no science experiment has ever done it. That $22 billion project in France hasn't done it. Nobody's been able to reach energy break even, which is more energy out of a fusion reaction than you put into it. That obviously is a problem if you're trying to put energy on the grid. And so where most people stand, I think is quite close to Q equals 1 at this point, quite close to energy break even. My guess is that a number of companies will probably get to break even this decade. But break even is kind of Everest base camp when you think about it, right? We need to get to commercial rates of fusion in order to actually have a viable power plant. And so everybody's talking about Q equals 1, Q equals 1, but that's just a step along the way to get to something that we could actually deploy onto the grid.
So your kind of value proposition as a company is that if you can make it work, it could be deployed way, way faster than any of these others, which are like, take 4 years to build the facility in each case, right? Is that roughly what you're trying to say?
Yeah, I mean, when you think about the fact that 20 years ago, none of us had an iPhone in our pockets, the reason that they're so ubiquitous is because they basically have a year-long design and build cycle. And when it takes 10 years to build a tokamak, and it's an extremely sophisticated system, it's not honestly that elegant of a solution, you can't expect to develop the technology fast enough to bring it to market in time. We have, a year design and build cycle and less than $1 million to do that.
So in other words, if you get past this Q equals 1, that will allow you to build systems in a year.
Yeah, I mean, today we're building, reactor cores in less than a year, yeah.
Okay, I think somebody else probably may have better questions than me on this. Anybody have a question or a comment? The thing about fusion, okay, there's a fusion questioner, okay. The thing about fusion that is great while we're waiting for the mic is if it works, it's kind of the silver bullet, right?
Yeah, it's kind of the silver bullet. I mean, it truly can massively produce electricity in a clean way without long-lived radioactive waste like fission. It is not fission in pretty much any way. There's no meltdown risk. And so you can generate energy very close to the actual consumers. When you think about the fact that 1/3 of the cost of energy is, transmission and distribution, being able to actually build nuclear, which is massive baseload generation, close to consumers, it's a game changer.
Okay, good. Go ahead.
Hi, I'm Nicholas, MBA student from Brazil. My question is, after we get to Q equals 1, is it harder to get to a state where we're actually deploying energy into the grid at scale? Is it easier? Do we know?
Great question. The beautiful thing about the sheared flow stabilized Z-pinch design, this approach that we're taking, which is kind of different from the status quo, is that there's a very clear correlation between the amount of current that you pass through the plasma and your Q, your reaction rate. In fact, there's an 11th power relationship. And so if you even incrementally increase current, you're significantly increasing your fusion output. And there's a very clear curve that we're tracking against as we continue to develop our technology, 400 kiloamps, 500 kiloamps. When we hit about 650 kiloamps, we expect to reach around break even, and then just beyond. And so it's scaling physics as opposed to, totally different physics and when you hit a mega amp, for example.
We do have to wrap, but the company is pretty much created by a bunch of professors at University of Washington, right? That's why it's in Seattle.
Yeah, the technology was spun out of the UW and Lawrence Livermore. And so it's been around. I mean, the Z-pinch has been studied for the last 20 years by these guys, and now we're real.
Well, very cool. Thank you so much for being here to talk about it.
Thanks.